Hello everyone, and welcome to Biopedia. This week we're going to discuss the Wnt Signalling pathway, spelt WNT, a vital pathway in development. Just a brief note before we begin, this pathway is going to involve the G-protein coupled receptors we discussed back in episode 3 and which we gave an example of in episode 4, so it might be worth checking those out if you haven't already. The origin of this bizarre name actually comes from two separate experiments. Experiments on the common fruit fly, Drosophila melanogaster, discovered that the wingless gene played a key role in the development of wings. Meanwhile, a similar gene was discovered to promote breast cancer when activated in mice. This was the Wnt gene. Eventually, it was discovered that both these genes encoded for members of the same particular family of proteins. The mergence of these two names, wingless and Wnt, was used to describe the new family of Wnt proteins. There are 19 distinct Wnt proteins in humans, which activate at least 3 signaling pathways within the cell. However, we are going to focus on just one of them, which is known as the Wnt/beta-catenin signaling pathway. Before we go on to describe the pathway, we need to talk about the structure of these proteins. There is an important feature of Wnt proteins which helps them carry out their role further downstream, namely the groups that are bound to them. 2 glycan groups and 1 palmitoleic acid, a carboxylic acid 16 carbons long, help to give Wnt proteins a shape that one paper described as hand-like, with the palmitoleic acid forming the thumb and the 2 glycans helping form the palm. I know it's difficult to visualize this with audio, but the reference for the 2012 paper discussing this will be in the description. Wnt's subsequent structure helps it bind to Frizzled, a G-protein coupled receptor in the plasma membrane of the target cell, and also a co-receptor which has the abbreviation LRP. And for the purposes of this episode, you don't need to know what this stands for. This binding subsequently recruits a protein which is usually inactive inside the cell, called disheveled, and activates it. Now, in order to be able to explain this pathway properly, I'm going to have to jump forwards a bit and then circle back around again. Cells contain a compound called beta-catenin, whose role among others is to bind to a family of proteins called the Lef1/TCF family and displace a repressor they are usually bound to called Groucho. Once this is done, beta-catenin can induce the transcription of genes that this signaling pathway is trying to transcribe. Its role, in brief, is to act as the effector of this pathway by activating transcription of key genes. Beta-catenin is constantly manufactured in the cell, which you might reasonably think means that these target genes are therefore constantly activated. However, the cell also manufactures a beta-catenin destruction complex. This complex is made up of 2 kinases, which each add a phosphate group to different locations on the molecule, and 2 structural proteins called axin and APC, which hold the structure together. The first phosphorylation event enables the second one to happen, which then marks the beta-catenin molecule out for eventual degradation. In effect, therefore, cells continually recycle beta-catenin when the Wnt pathway is not activated. I'm trying not to overload you with names in this episode, so again, the sources in the description contain visual guides. At this point, we return to the receptors we left activated in the membrane and the now active disheveled protein. Disheveled recruits the destruction complex to the membrane, where it can take part in reactions set off by the Frizzled and LRP receptors. These 2 receptors form a complex and, through a mechanism that still isn't entirely understood, induce the kinases in the destruction complex to phosphorylate the tail of LRP rather than beta-catenin. Axin, one of the structural proteins of the destruction complex, is also phosphorylated and thus changes its shape, meaning the complex can no longer bind to beta-catenin and is inactivated. This allows beta-catenin to influence the transcription of genes we mentioned earlier. So, a quick summary. Binding of Wnt ligands to 2 key receptors in the cell's plasma membrane induces the deactivation of a complex that would ordinarily degrade beta-catenin. The prevention of this degradation allows beta-catenin to induce transcription of effector genes, thereby allowing Wnt ligands to have an impact on development. This has obviously skipped over some detail, but my aim is to provide a summary rather than in-depth analysis. As always, thank you for listening. I've tried to limit the number of names in this episode, but I'm afraid that any discussion of a signalling pathway is always going to be swamped with them. I hope that the sources in the description will go some way to making what I've said a bit easier to digest. We'll be back to our usual level of detail in future episodes. If you would like to suggest future topics, have any questions answered, or leave a comment about the show, feel free to contact us at biopediapodcast@gmail.com. Until next time, have a great week.